Now that we have a better idea of how my hexadecimal relay calculator works, let's take a look at the individual boards and see kind of how they're laid out. Right in front of you is all of the boards that are used, and each one of these you can see connects to the motherboard through these pin headers on the bottom, and we'll take a look at the motherboard a little later. Starting over here, we have the display and input board. These are the two display registers that hold the 7 bits for the 7-segment display here. This is the input decoder, so whenever I push a button here, this decodes it into 4 bits of binary. These 5 boards here are the 7-segment decoder, so it takes 4 bits of binary and decodes it into 7 bits to be stored in the display register here that will ultimately end up getting displayed on this. This back here in the corner is the control board. It runs the different operations, allowing certain boards to read or write whenever we press a button. These two boards are the mic and November register, the M and the N register. These are the two boards that hold the 4 bits that we're doing math on. This is the exclusive OR board. This inverts the binary that's in the November register so that we can do subtraction. And then these final 4 boards here are the arithmetic boards that do the addition. This is the motherboard that all of the individual cards plug into, and you can see they plug into these female pin headers right here. And nobody sold a pin header that was quite the right length, so I actually ended up taking 2 pin headers and having to chop and file them down to get the right length. And so you can see, we have individual cards set up, and you can actually see the pathways that have been cut for the traces on the bottom through the top, which I think is kind of a neat feature of this. Now this, like all the other boards, is a single-sided PC board, so anytime that I needed to have traces cross each other, I had to run a jumper wire. So you can see the jumper wires up here, along here, and the back of here. Now the control board mounts in this very back spot here, and that's quite important because it controls certain things in this direction as well as in this direction. So it will run a signal down to here to enable the display register to save, or it sends signals down to this way to allow the arithmetic unit to output its answer onto the data bus. Now on the far right here, on both sides, you can see there are some traces. It is power, ground, and then the 4 bits of the data bus. And you can actually see the jumper wires for those right over here. There's 5 jumper wires because one of them didn't need a jumper to cut across. And then power and ground also feeds into our little barrel jack connector here in the back. So to just flip it over, we can get a good look at the traces on the back and how they were cut out. You can see I put these 4 bolts through the board here to kind of act as feet for the board. I would like to put little rubber caps on that someday so that way it doesn't slide around, but it works well enough for now. And then you can see that the mill just takes a solid copper-clad piece and then just cuts away the traces that are unnecessary. It isolates them from the rest of the copper cladding. This is the display and input board. You can see here that we have just a bunch of buttons lined up here on this side and then our 2 displays set up here. You can see some pin headers pushing through here, but those are really just to mount it. They don't actually connect up to anything. So if we flip it over, we can get a better look at kind of what's going on. It looks a little chaotic, but there is a rhyme to the reason. 5 volts goes into each button, and then each button has its own individual output, which is what runs along this bottom edge right here. And then, we have power and ground on this side. And then these pins right here are the display pins. So there's 7 pins for the display, and then 1 for negative, and then 1 for the +1 carry bit that we see. These 2 boards are the 7-segment display register. So you can actually see that with the capacitors here, there's 7 capacitors. And so that means that each pair of relays and capacitor, this little trio here, represents 1 segment of the display. If we flip one of the boards over, you can kind of get an idea of the chaos that is the backside of the board there. Though this is a little different than the set reset latch that I demonstrated in an earlier episode. And that's because we have this, this capacitor here. And the main point of this capacitor is to allow us to reset the bit that's in there every time we write a new bit to it. So if we were trying to, write 0 when there's a 1 in there, we could end up in a situation where that 1 doesn't get deleted. So every time we write something to this register, we clear the register out. And then when we stop writing to the register, this capacitor holds the contact open a little bit longer to make sure that the new bit that's getting written in actually saves. Without this capacitor, the latch never actually latches because it cuts off at the same time as the write function ends. So this type of register setup is used for the 7-segment display, but it's also used for the 2 4-bit registers that we use for the Mike and November register right here. So you can see that we've got these 2 boards set up here. This is the Mike and the November register, and they operate under the exact same principle. You can see again that we have our 4 capacitors here, and then this kind of, dual combo of relays here. So the Mike and November register and the display registers are all built identically. This is the input binary decoder board. You can see here that it's essentially just a bunch of diodes. And the diodes were a little fatter than I was expecting, and they didn't quite fit where they were supposed to be, but it ends up working just fine with no problems. And so what essentially happens is that whenever you push a button, 5 volts comes into one of these pins, depending on what button you pushed. And then it travels out of that pin into a series of diodes. So you can see here that this series of diodes here comes out of the diode and then jumps over to here, here, and here. And so that 5 volts essentially gets split up into whichever corresponding binary it's supposed to be. So if we look at the back, we can get a kind of a closer idea of what's going on here. So you can see each line comes up and then breaks out into a couple different spots depending on which diodes go where. This is the first board that I soldered up, and I was not doing very well, so it looks super messy, but it does work. Once it goes through the diodes, it hits up this kind of 4 lines that run along right here, and these are the data bus. 5 volts goes in, gets broken out through the series of diodes, and then puts 5 volts on whichever line of the data bus is supposed to get 5 volts to represent a logical 1 on that line of the data bus. This is the control board. So essentially this starts off a kind of multiple delay setup to essentially start a ring counter. So it does a 2-step ring counter. And then the 3rd step turns off the 2nd step. So it sounds like there's 3 clicks, but really stuff only happens on the first 2 clicks. And on each click of that, it sends signals out on these pins down here that go to the various bits, to the display register, to the arithmetic unit, or to the Mike and November register to either enable or disable those at the appropriate timings. Now, all of these diodes over here in these pins are essentially, whenever you press a button, we want to kick this off, but it doesn't matter which button you press. So if you press a 1 or if you press a 9 or an A, each button kicks this off the same. So the buttons all come in through these individual pins, go through these diodes, and then on the opposite side of these diodes, they all connect into one line that goes off and kicks off the start of this delay thing here. And then these extra relays on this side are for switching whether we're enabling the registers for when we push a button to store them, or whether we're enabling the ALU. So it switches back and forth depending on which buttons we press. So the plus, minus, and equal buttons also come into here and use this board to do their individual things. So if we flip it around, you can see actually this one has a bodge wire on the back. I made a mistake in the design, and instead of cutting a whole new board, it was a lot easier just to do a bodge wire there. And I ended up having to slice through a trace and then solder in the bodge wire. But it seems to work. And this was actually the second control board that I ended up building. The first one ended up not saving data correctly at all at any point in time. And So I had to completely redesign and change my thinking about how to do the display board. And as a result of that, we ended up not using the static RAM boards that I mentioned in the previous episode. But here you can see this is where all the individual pins come in. They go through the diodes, which are on the opposite side of that, and then all the diodes go together right here. And then over here we have the equals. These 5 boards are the 7-segment display decoder boards, and they work under the same principle as the binary decoder board that we already looked at, except they kind of go in the opposite direction. So the 4 bits on the data bus come into this group of relays on each board, and then depending on what those 4 bits of relays are, this group of relays will open up or remain closed. So these kind of decode the binary into a single thing. So for example, here, if we flip it over and we take a look at this board here, you can see that there are 4 lines up top here that feed into the series of diodes, like that all of these have here. And depending on which of the 4 data bus lines are high, we engage or disengage certain relays. And if the right combination of bits on the data bus are high, then the relay will open up and allow 5 volts to travel down the appropriate line. And then when the 5 volts goes down that line, it runs into these diodes that then break that out, and each one of those diodes goes to these 7 pins on the bottom here that send the appropriate 5 volts to the 7-segment display to display 1, 2, 3, 4, 5, 6, 7, 8, 9, or A, B, C, D, E, and F. So these 5 boards aren't reliant on each other, and you can remove one board and the remaining 4 boards will work just fine. But it took 5 boards and able to cover all of the binary data from 0 to 15. So one board only really covers 2 or 3 numbers. I think there might be one board on here that covers 4 numbers. So each board only covers 2 or 3 numbers, and then the 5 of them together end up covering the entire range of 0 to 15. These 4 boards are the arithmetic boards. They're essentially identical. They just have slightly different pinouts to access different bits of information coming from the mic register and the November register. Each board is just a 1-bit full adder, so it takes 2 inputs, 1 bit from the mic register, 1 bit from the November register, and a carry in, and then it performs the math on it, and then it outputs the answer onto the data bus, or it outputs the carry into the next board. So for example, this board will take bit 1 of the mic register and bit 1 of the November register. It will do the math on them, and if there's a sum, it will put it out into the data bus. If there's a carry, it'll put it out on one of these pins over here as an input for the carry in of the next board. And in that way, the boards kind of cascade into each other. So if we flip a board over, we can kind of take a look at what that 1-bit full adder looks like. Remember, it is just essentially 2 exclusive OR gates, 2 AND gates, and an OR gate. And there's a really elegant way of combining all those. Although the OR gate, as you can see, is just two diodes. And then the AND gate is integrated into the exclusive OR gates, which allow us to have a very compact board here. And actually the full adder is just 4 relays. The additional 2 relays on the side here are just an enable relay that allow the output to be put onto the data bus. So that way we don't have a data bus conflict, because these are constantly doing math on whatever is in the mic register and the November register, even if we haven't hit the equals button yet. This is the Arithmetic Unit exclusive OR board. Essentially, it's just 4 exclusive OR gates set up in a series here. So you can see that each of these 2 relays represents 1 exclusive OR gate, and it'll take 4 bits from the the November register, runs it through an exclusive OR, and then outputs them on this one for the arithmetic units to use. If we haven't hit minus, essentially the 4 bits comes in and passes through with no change. But if we have hit the minus, then it inverts it. And these 2 relays here are the latch for the minus. So whenever I hit the minus button, these 2 relays latch, which kick off our exclusive ORs there to invert it. So it's a fairly simple board. As you can see with this one as well, I made a mistake on the back and had to create a bodge wire to fix it, but that fixed it right up, and it seems to operate with no problems whatsoever. So there we go. I've got all the boards back in place on the motherboard, and it does still work correctly. As you can see, 3 plus 1 is equal to 4 there. Now it should be noted that each segment of boards doesn't have a particular order, but they have to be put within their appropriate segment. So for example, these two boards up front here can be flip-flopped and it doesn't make a difference, but if I put one of these boards over here, it won't function correctly. The same with the arithmetic boards here. Any of these 4 arithmetic boards can go into any of these 4 slots, and the calculator will still work totally fine. Same with these 5 decoder boards here. But you need to put them into correct order. So this has to be, the 2 display register boards, the decoder board, the 5 decoder boards up here, the 4 arithmetic boards have to go within these 4 slots. The exclusive OR board absolutely has to go in this slot. Since it's only one of them, it has to go right there. The same with the control board in the back here. Since there's only one of those, it has to go right there. And then the Mike and November register can flip places as well. And then these are the static RAMs that we're going to remove, and I think we'll put something a little interesting there. So we might put a little switch on there with some LEDs to show us what's happening on the bus, and maybe what some of the control signals are doing. So that's something that we'll tackle in the next episode.